Hello students, welcome to physics class. Today we are starting a new chapter in physics, that is electromagnetic induction, chapter number 6 from NCERT textbook. In the last chapter, that is moving charges and magnetism, we learned that the magnetism can produce with electricity. That is, every current carrying conductor produce a magnetic field. In this chapter, we are going to learn how electricity can produce with the help of magnetism. So before going to discuss that concept, let us see or let us introduce a new physical quantity named magnetic flux. Hope you remember in this chapter electrostatics we learned electric flux. Now let us see what is magnetic flux. The magnetic flux through any surface placed in a magnetic field is the total number of magnetic lines of force crossing the surface normally. That is the magnetic flux. The magnetic flux through any surface placed in a magnetic field is the total number of magnetic lines of force crossing the surface normally. Here we have a surface, let us say A is the area of that surface and this is the normal to the surface. Now this surface is placed in a magnetic field. Let us say the strength of magnetic field is B. You see that the angle between the normal to this plane and the magnetic field is theta. The flux link or the flux associated with this surface can be written as the flux phi is equal to B into A cos theta. B A cos theta. B is the magnitude of magnetic field, A is the area, and theta is the angle between the normal to this area and the magnetic field. So we can write the flux as the dot product between the magnetic field vector and the area vector. The phi is equal to B dot A. Here area is taken as a vector because the direction of area is very important, which decide the magnitude of magnetic flux. So that's why we taken the area as a vector quantity. And the direction of area is in the direction of normal. So flux is equal to phi is equal to B dot A. As it is the dot product between the magnetic field and area vector, is a scalar product, so it is a scalar quantity. Magnetic flux is a scalar quantity. There is no direction for the magnetic flux. See, the SI unit of magnetic flux is Weber, and it is denoted with a symbol capital W, small letter B. That is the SI unit of magnetic flux. SI unit of magnetic flux is Weber, and 1 Weber is equal to 1 Tesla meter square. 1 Weber is equal to 1 Tesla meter square. We know that the unit of magnetic field is Tesla and unit of area is meter square. So Tesla meter square, that is the SI unit of magnetic flux. And see the 1 Weber, we can see the flux associated with a coil is 1 Weber. That is 1 Weber is the flux produced when a uniform magnetic field of 1 Tesla acts normally over an area of 1 meter square. 1 Weber is the flux produced when a uniform magnetic field of 1 Tesla acts normally over an area of 1 meter square. So one more unit is there for measuring this magnetic flux. That is a smaller unit, that is a CGS unit, and that is Maxwell. See, the relation between the Weber and Maxwell is 1 Weber is equal to 10 raised to 8 Maxwell. 1 Weber is equal to 10 raised to 8 Maxwell. And the dimension of this magnetic flux is equal to M L raised to 2, A raised to minus 1 and T raised to minus 2. That is the dimension of magnetic flux. We'll see that when the angle between this magnetic field vector and normal changes, the magnetic flux also changes. When the normal is parallel to the magnetic field, or otherwise we can say the plane is perpendicular to the magnetic field, so the flux is equal to BA cos 0. The flux become maximum. Flux phi is equal to BA cos 0. It means all the magnetic field lines are perpendicular to the plane. Then the flux is maximum. BA cos 0. 0, that's the angle between normal and the magnetic field. The flux is maximum. And the flux is minimum when the plane is parallel to the magnetic field lines. When the plane of this area is parallel to the magnetic field lines, we can say that normal and the magnetic field makes an angle 90 degree. So we can write as BA cos 90, cos 90 comes to 0. So flux is minimum by that time. So the flux varies with the when the angle between the magnetic field and normal changes. Now let us discuss what is electromagnetic induction. In 1831, the scientist named Michael Faraday experimentally proved that whenever the magnetic flux associated with a coil changes, an EMF is induced in that coil or a current is developed in that coil, and that phenomenon is known as electromagnetic induction. The phenomenon of production of induced EMF and hence induced current due to change of magnetic flux linked with a closed circuit is called electromagnetic induction. So the phenomenon of production of induced EMF and hence induced current due to change of magnetic flux linked with a closed circuit is called electromagnetic induction. Let us see some of the experiment conducted by Michael Faraday to demonstrate this phenomenon of electromagnetic inductions. That is, here we have a permanent magnet, a bar magnet. This is north pole and south pole. So some of the electric field lines, some of the magnetic field lines due to this magnet is shown here. They are starting from the north pole. And here, very close to this, we have a conducting coil and a galvanometer is connected to this coil. So this is a closed coil. When the magnet is moving towards this coil, that is when the north pole of this magnet is moved towards this coil with a certain velocity, say v, then we can observe that there is a deflection in this galvanometer. That is, the needle in this galvanometer deflect right of 0. 0 is at the center, so towards right of that 0. And in the next time, when you are moving this north pole away from this coil, it is observed that there is a deflection in this galvanometer to the left of 0. That is, when the north pole is moving towards this coil, there is a deflection in this galvanometer that is right of 0. And when the north pole is moving away from this coil, it is observed that there is a deflection to the left of 0. So instead of this north pole, suppose if you are moving south pole towards this coil, the deflection will be towards left side. That is, if you are moving the south pole away from this coil, we can see that there is a deflection towards right side. Then the next time, suppose there is no relative motion between this magnet and coil, then we cannot observe any deflection in this galvanometer. The magnet is fixed, the coil is fixed, there is no relative motion, so the galvanometer showing a 0 deflection. So the next time, suppose we are fixing this magnet there, we are not moving this magnet, instead we are taking this coil towards this magnet with a certain velocity, say with a velocity v. Again, we can observe that there is a deflection in this galvanometer. So in all this experiment, there is a relative motion. Whenever there is a relative motion between this magnet and this coil, some current is produced in this coil. That's why the galvanometer showing some deflection. The galvanometer indicates the presence of current. Whenever there is a relative motion between this magnet and a coil, there is a production of current in this coil. So we can say the reason for this deflection or production of current is whenever the magnet is moving towards or away from this coil, the flux associated with the coil is changing. Here, when we are moving the magnet towards this coil, the flux increases. When you are moving this magnet away from the coil, the flux decreases. So here there is a production of current. Whenever the flux associated with the coil changes, current is produced. In this case, there is no current because there is no flux change. The flux is constant here. There is no relative motion between the magnet and the coil. That's why there is no deflection. So in this case, even the magnet is fixed, the coil is moving towards it. So the flux associated with the coil is increases. That's why there is a production of current in this coil. So however, we can conclude that faster the relative motion, if you are increasing the velocity of approach, we can say the faster the relative motion between the magnet and the coil, greater is the rate of change of flux. If you are moving this magnet towards the coil very fast, the rate of flux also increases and more current is producing. So we can say faster the relative motion between the magnet and the coil, greater is the rate of change of magnetic flux linked with the coil, and large is the induced current. The magnitude of induced current depends on the how fast the flux is changing or the rate of change of flux. So in all these cases, if you are moving the magnet or coil very fast towards or away from the magnet or coil, the magnitude of current developed is also increases. Let us see another experiment here. We have a rod and two coils are winded on the same rod. Here in the first coil, that we can call as a primary coil, one battery and a tap key and a rheostat is connected. In the secondary coil, we have only a galvanometer. And we can observe that when you are tapping this key, that is when you are closing this tap key, it is observed that there is a deflection in this galvanometer. There is a momentary deflection. We are pressing for a long time, there is no deflection. The galvanometer comes to zero. The needle of the galvanometer comes to zero positions. Whenever you are releasing this tap key, by the same time, we can observe that there is a momentary deflection in the galvanometer, just opposite direction. When you are closing, if the deflection is towards right side, when you are releasing it, there is a deflection towards left side. Here, when you are closing, what actually happening is that current is passing through this coil, primary coil, and it produces a magnetic field. So the neighboring coil is in a varying magnetic field. The neighboring, that is secondary coil, is in a varying magnetic field because initially there is no magnetic field for this coil. When current is passing through this coil, we can say that a magnetic field is developed and the secondary coil is in a varying magnetic field. That's why there is a deflection. But if the key is pressed for a long time, there is no variation of magnetic field, so there is no flux change. What happened when you are releasing the key? When you are releasing the key, the current decreases and magnetic field decreases. Again, the magnetic flux of the secondary coil is varying. That's why when you are releasing the key, then the current is induced in this coil. These are the experiments conducted by Michael Faraday to demonstrate the electromagnetic inductions. The experimental result of Michael Faraday is concluded as the laws of electromagnetic inductions. Actually, there are two laws in electromagnetic induction. One is Faraday's laws of electromagnetic induction and other one is Lenz's law. Let us see what are the laws of electromagnetic induction. The first, the Faraday's law of electromagnetic induction. There are two statements in Faraday's law. The first law states that whenever the magnetic flux linked with a closed circuit changes, an induced EMF and hence induced current is set up in it, which lasts only so long as the change in flux is taking place. That's the first law. Whenever the magnetic flux linked with a closed circuit changes, an induced EMF and hence an induced current is set up in it, which lasts only so long as the change in flux is taking place. When there is no change in flux, there won't be any induced EMF and induced current. And this phenomenon, we know that we calling as electromagnetic induction. Now see the second law. The second law, the magnitude of induced EMF is equal to the rate of change of magnetic flux linked with the closed circuit. The second law is associated with the magnitude of induced EMF. The magnitude of induced EMF is equal to the rate of change of magnetic flux linked with the closed circuit. That's why we are writing the magnitude of induced EMF is equal to d phi by dt. If d phi by dt is the rate of change of magnetic flux associated with the coil, that is E is equal to d phi by dt. Now see the second law of electromagnetic induction. That is actually our Lenz's law. From Faraday's law, we are getting only the magnitude of induced EMF. So in order to find the direction of induced current produced because of the induced EMF, we have to use Lenz's law. See the statement of this Lenz's law. This law states that the direction of induced current is such that it opposes the cause which produced it. That it opposes the change in magnetic flux. We know that the cause of production of induced EMF is the change in flux. So the induced current flows in such a way that it opposes the cause which produces it. That the direction of induced current in a circuit. So by Faraday's law, we can write the magnitude of induced EMF is equal to d pi by dt, the rate of change of flux. On account of Lenz's law, we will write this induced EMF E is equal to minus d phi by dt. So this minus sign in this equation shows that the induced current tries to opposes the cause of flux change. So that's the significance of this minus sign. Now let us demonstrate or let us illustrate Lenz's law. How can you predict the direction of induced current by using this concept of Lenz's law? For that, here we have a bar magnet, north pole and south pole. We are moving this bar magnet towards a closed coil. The end of this coil is connected to a galvanometer. We are moving this north pole towards this coil. So what actually happens that you know that there are magnetic field lines for this magnet. Whenever we are moving this magnet towards this coil, the flux of this coil increases. The flux of this coil increases. So according to Lenz's law, the induced current tries to oppose the increase of flux. How can it oppose? The cause of increase of flux is the north pole is approaching towards it. So what actually coil is doing is that it sends a current through this coil in such a way that it want to oppose the motion, oppose the approach of north pole towards it. What can do? By produce a north pole, it try to repel the magnet. So on the side of this magnet, it will produce a north pole. So to produce a north pole on the side of the magnet, the current should flow in the anti-clockwise direction. So we can explain the direction of current by using the Lenz's law. Now see the second case. Suppose we are moving this magnet, the north pole of the magnet, away from this coil. By the time the current is flowing in clockwise direction. How can we explain? The cause of production of induced EMF is the flux of this coil decreases. When the north pole is moving away from the coil, the flux decreases. So the coil want to send the current to oppose this motion of this magnet. The flux decreases. So it sends a current through this coil in such a way that it will produce a south pole in the side of the magnet. It will produce a south pole in the side of the magnet. So what happened? It attract the north pole. It attract the north pole. So we can reduce the decrease of flux by doing so. So the direction of current when the north pole is moving away from it is in the clockwise direction. So by using this Lenz's law, we can explain the direction of current produced whenever the flux of the coil is changing. So we can say that the Lenz's law is valid and is a consequence of law of conservation of energy. We know that when the magnet is moving towards it, already the coil produces a north pole in the side of the magnet. So if you want to move this magnet towards it, there is a repulsion from this north pole. there is a repulsion of this coil. So we want to do an external work to move this magnet towards it. That work is actually converted as electric energy. So electric energy is produced by the work. Work is converted into electric energy. In this case also, when we are moving the magnet away from this coil, a south pole, the coil produces a south pole in the side of the magnet. So if you want to move this magnet away from this coil, there is an attraction from this coil. So work has to be done. This work is converted as electric energy. So that why we told that the Lenz's law is valid and is a consequence of law of conservation of energy. That's all today. Thank you.